Because now we're used to, you ask ChatGPT a question, it answers your question. But that's actually not the natural way that transformers work. The natural way that transformers work is that you have a sentence and it completes the sentence. And the kind of golden bullet was what's called zero-shot completion. Zero-shot completion is essentially what we have now, right? Which is like, I ask you a question, you answer the question. The way they ultimately found how to do that is to take manually curated data sets of what's called supervised learning, have people create specific data sets designed around accomplishing a specific goal. And in this case, it would be like QA data sets, right? So it'd be like, here's a simple question, here's how you should answer that question, right? So it's essentially creating this pattern to specify in these later steps for ChatGPT to follow. That ChatGPT sees a question, it knows it needs to reply to that, not by drafting another question, but by actually answering the question.
The Quantus Podcast.
Welcome, everybody, to the Quantus Podcast. We're here with a very special guest today, Brian Chau. And I'm actually just, getting to meet him on camera. So why don't you tell us a little bit about yourself, Brian?
Yeah. So I kind of got into this whole world of machine learning when I was like 12 or 13. I went to the Canadian Nationals for computer science, and then the whole like competitive programming community and the machine learning community was kind of interlinked. So a few years later, I also went to U.S. Nationals. I'm a dual citizen. There, my coach was Mark Chen, who's now like head of agent research at OpenAI. I think like Horace Ho was there, who's the founding engineer of Thinking Machines. And it's just like a really tight world. So I get into this machine learning pipeline from competitive programming. And that's also why like all of these AI companies are obsessed with doing competitive programming problems, by the way. It's like the same people. And then I do a degree in pure math at the University of Waterloo. I focus on random graph theory, which is not that useful of a field in practice. And then
You take the AI and you just scramble its brain, and then you try to make it go back together again.
Yeah. And then I work at a few AI startups. I end up starting this nonprofit because a lot of people I knew were very worried about the kind of AI regulations that were coming out of the Biden administration. So I start that. It's a nonprofit called Alliance for the Future. I run that for like 2 years. And
Alliance
then
for the Future.
Yeah. And then I leave and I come here to Singapore to network school, and I join network school. That's the career path.
That's a very interesting career path. Just for the listeners, when you say competitive programming, what exactly is that?
Yeah. So at a high school and university level, sometimes for like the very top people, even past that, there are these like really selective contests in which you're given a few hours to solve these theoretical computer science problems. It's quite similar to the Math Olympiad system, if you've heard of that, which a lot of people, it's a similar setup where you get locked in a room with like a few hours, usually 3 to 5 hours, and you have to solve usually 3 math problems, and you have to write proofs for them. It's a similar thing where instead of writing proofs for math problems, you have these theoretical computer science problems, these algorithms problems, and you actually have to write code to execute the algorithms.
Okay, so and you say theoretical computer science, but you are writing. You're writing code.
You're writing code. You're not just like proving complexity or something. You're writing code, although a lot of the time, like the complexity matters, and you're basically trying to execute this like algorithm at scale that solves this like complicated problem.
Can you give me like a rough idea, like what kind of things are we talking about here?
Yeah, a common like entry-level algorithm, usually the first algorithm that you learn is something called Dijkstra's algorithm, which is taking this problem where you're trying to find, essentially like you're trying to create Google Maps, right? You're trying to find the shortest distance between 2 points in an interconnected network. So you have these things called nodes, which are essentially like places, and you have these things called edges, which are essentially roads between the places, and the roads can take different lengths of time to travel. And then you're basically saying, how do I get from place A to place B in the shortest amount of time?
So you're doing these competitive programming, and the pipeline goes from there into AI, machine learning, and so what attracted you to machine learning? Why was that so interesting?
I think for the type of person who likes thinking about theoretical problems, machine learning is really a kind of nerd snipe, right? It's something that just like pulls you into the pit. And for the time, it really did feel like a pit in, like, 2014, 2015. I mean, even then, there was a lot more progress compared to before. But it was sort of this more academic thing. It was more so something you did in theory. And then, like, maybe in practice, you would get, like, a data science job running, like, delivery time optimization at Amazon, right? That was like maybe the payoff to that. So I really didn't expect in my wildest dreams, all of the $100 million machine learning contracts that you have now.
Do you think that's real? I wonder how much of that is marketing. Like, do you know anybody who got a 9-digit machine learning contract? That seems quite extreme,
I think 9 digits, that is a bit extreme. Or like, I don't know, that at least seems rare to me.
Sure.
But I think, like, in general, like, machine learning engineers at Google and Meta and OpenAI and so on are, like, quite well compensated at this point.
Yeah.
Maybe not that well compensated, but, like,
I would believe millions.
Yeah.
That seems
millions, tens of millions isn't rare either.
And what's the difference between, say, because I guess, you can implement machine learning algorithms, but most of the time, if you're using machine learning, you're using some library, right? Like scikit-learn or, maybe PyTorch or something like that. So, but developing the new algorithms, I suppose, is where the real juice is, or maybe optimizing existing algorithms.
More so optimizing existing algorithms. I think it's actually quite a different experience working at machine learning startups and one of the larger labs. Because at a larger lab or even like a medium-sized company, there's usually a thorough production pipeline, and you're essentially taking this enormous machine, this enormous like infrastructure project, right? This literal billions of dollars worth of project in terms of talent, in terms of hardware, in terms of energy, and you're taking like 1/1000th of that project and making it work the best way possible. A lot of the time, this is actually something that I worked for at like a medium-sized startup, recently got acquired by AMD, called Untether, is working on like the data size of like these what are called weights, right? So this is a field called quantization. The idea is that the way that we run machine learning algorithms now, or less so now, but at least a few years ago, just use much too large of a data type.
Like too much precision.
Yeah, exactly. Too much precision. So computers will store like a certain number of binary digits, right? You can think of them as similar to significant digits in normal real life numbers, I guess.
Sure.
And it turns out that in order to run these machine learning algorithms, you didn't actually need that many digits. And of course, if you have fewer digits, then adding them together or multiplying them takes less time. So you can optimize the data type in order to optimize the overall performance. And so you'll see tons of these like tiny things, like, there are people who just work on how the data is like loaded onto these different machine learning hardwares, right? Like NVIDIA's GPUs. You'll have people who work on the specific, what's called, attention head, this like multiplication step and different ways to optimize it. So I think if you're working on at a large lab, mostly what you're doing is you're taking this like very precise, like scalpel-like operation, and you're making it go as smoothly as humanly possible.
Right. So in the case of like, if you're just optimizing for accuracy, maybe, the more precision, the better, but you also have to optimize for how long does it take to train, how large is the model on disk and things like that. And it's sort of like, I guess it's always floating point numbers, right?
Yeah. It's typically like literally floating point numbers, FP8 or FP16, which is what's typically used even on like, or not what's typically used, but like it follows the same pattern as what's typically used of like 32-bit floating point numbers, but just half the number of bits. There's another mixed precision data type called BF16, which is kind of a modified version of a floating point number. But
it's like, if you have your learning rate, which is like how big of a step you take through the sort of parameter space, and if that's like much bigger than the precision, then it's sort of like, okay, you're skipping over a ton of significant bits. with every step you use to update the weights. So, how important could they possibly be?
Yeah. What's really interesting, and this is why you have a divide. So in modern times, when I say modern times, it's funny. I mean like post 2023, like post ChatGPT.
It's quite modern. I will tell you that.
You have like in the real world you have before Christ and after Christ. In the AI world you have before ChatGPT and after ChatGPT.
Wow.
So modern times. So after ChatGPT, there's a gap between what's called training time and inference time. So when you're actually training an AI algorithm, people will use a different precision than when you're actually running it, when you're actually using ChatGPT to answer your questions. And the reason for that is actually basically what you described, this process where you're correcting the errors, right? Where you're going through the gradient descent, which is the sub-algorithm that allows, that's like the learning part of machine learning, right? Which allows you to correct the weights and to use all of this data to improve your algorithm. That part requires a much more continuous improvement, right? Because as you're correcting, you're kind of many people visualize this as you're kind of going up the slope, right? And so you need these.
I like to visualize it going down the slope.
Yeah,
because I just imagine water flowing downhill. But anyway, go ahead.
Yeah, well, you're going down the slope, but you need that slope to exist, right? You need that kind of continuous connection. And if the data type is too small, you kind of have these like jumps where the water can't really flow because there's just like a hole between where it should flow.
Right, so it's almost like you have like an image and it's very pixelated.
Yeah,
and so
exactly.
Then, it doesn't look like a nice diagonal. It's like, or it's like the color looks weird because of how the low resolution. So we were just working on some ZK stuff today, and one of our team members used to work on ZK for AI. It was like and it's sort of like one, it's two cutting edge technologies put together, but also you end up getting this. You have to prove, like in order to build these proofs, you have to import this, the machine learning model to some extent into this very opinionated and in many cases impractical compute platform. And so you get like sort of sometimes a quadratic number of gates in the number of parameters you have. So you can be really extreme in terms of the demands on it. But I just, they said they used quantization to sort of make it easier for the ZK system to reason about it. And I thought that was interesting because in ZK you have to put everything into a field element. Like there's no floating points, there's no ints, there's no, everything has to be a, whatever field element they choose. So it makes certain things like much more difficult or impractical and certain things easier. But how much like does it always have to be a float for the neural for the weights? Can it be some other data type? Like
so what we like actually mean by float in like just computing in general, right, is that we essentially have like some number of bits that are dedicated to the order of magnitude of a number, and some number of bits that's dedicated to the actual value of a number, right? So if you have like 10 to the negative 10, right? Or let's say 2 to the negative 10, right? All of those bits, all the information when you have 2 to the negative 10 are stored in the bits that determine the order of magnitude, right? So think of scientific notation, right?
Right.
You might have like 1E9, which is 1 billion, and that's like 10 to the power of 9, right? And you have something similar, right? Of course, with computers, it's 2 instead of 10, right? It's like 2 to the 10, but you have one part that's dedicated to the exponent, and one part that's dedicated to the number itself. So if it's like 2,134, right? The decimal equivalent of this would be like 2.134 times 10 to the power of 3, and then you would have some equivalent in binary. I can't do the conversion in my head right now.
Sure, but yeah. So I remember like in chemistry, I think is the first class where they introduced this significant digits thing, and it was kind of like, okay, yeah, if you put it into the calculator, it gives you all these digits, but actually realistically, your equipment has only a certain level of precision or a certain sampling rate, and so you should only store so many of that so that you don't over-represent the precision of your answer.
Yeah, and you get the exact same thing with machine learning algorithms where you'll only store so many digits. And the idea is, and it's interesting, there's a kind of trade-off here But the idea is that in general, usually the less significant digits don't matter as much, and you won't get that much of a difference in what your outcome is on what words ChatGPT will give you if you just drop the last digit of unquantized space. But there's all sorts of quantization to either change things to integer formats, like pure integer formats, to change things to other data type formats for particular kinds of hardware. There's a lot of interesting quantization projects out there, aside from just shaving off, one or two orders of magnitude of precision.
Sure, and I think if you zoom out into the topic of okay, so how do you just make this model smaller? There's the model model compression, right? Which is and we were talking about in a previous podcast, dreams, like human dreaming and memory consolidation. Of course, it's like you get this kind of like lossy compression of your memories, and which I feel like is kind of, it's kind of what the neural network is doing to begin with, because you have the amount of data you have is greater than typically than the number of neurons you have.
Yeah.
Otherwise, you would just memorize the data by sticking each one in a neuron, right? So then you end up having so somehow like the same information has to get, or different pieces of information have to get folded into the same neuron and has to represent multiple things, and so it creates this connectivity. But is there anything like sort of like, I mean, I know that sometimes they try to train a smaller model off of a bigger model, but I don't know, maybe you can speak about that.
Two things there. This is like a fascinating area, and the analogy you give is exactly right. It's actually like a big problem if you don't have enough data. This is more so an early machine learning problem, but it's like a huge problem if you don't have enough data points for the size of your machine learning network, because exactly the thing you said will happen. It's called overfitting in the machine learning world, where actually it'll learn much worse if you have many more parameters per data point, because exactly the thing you said will happen. It'll assign more parameters or it'll assign more neurons to exactly one feature or exactly one request, and then it actually will fail to generalize, right? So,
right,
so
but this is also
things outside of the data, and it can't do it.
Sorry. This is also how you get the universal approximation theorem, right? Is be like, well, if you have enough neurons, you could just memorize any function.
Yeah, you just add more epicycles. Yeah, exactly.
So I don't know. I think the whole, because I think we've all met students in school, that sort of like overfit, right? They sort of like learned exactly what you needed for the test, and then as soon as the test's over, be like, okay, that's gone. I'm gonna forget about it. I don't need to use that in my life. What's the next pile of stuff to put in? Yeah, I mean, there's a lot in there. I think when ChatGPT first came out, there was this kind of like a lot of fear associated with the wonder. People were like, "Oh, this is amazing," but they're also like, "Uh-oh, is this Terminator style Skynet?" And I think there was a kind of like the potential for some kind of dark timeline of AI emerging, where basically one company or one group got complete monopoly on the AI and sort of used it to just dominate the world. And I think that now there's a lot of competition, there's a lot of open source, so I don't see, they might be a little bit better than what's open source, but I don't think it's going to be this like, fundamental, it's not going to be like a speciation event, and so I'm happy about that, salute to all the open source people.
Yeah, it's really competitive, and I think that as you kind of start to hit some diminishing returns, it becomes like harder and harder. Small mistakes matter more and more. They kind of really add up. And so there's, in one sense, there's like two things happening, right? On one sense, at a pure kind of volatility level, it's like harder for Meta to catch up with OpenAI, or like harder for DeepSeek or Qwen or Mistral or any of these open source AI companies. On the other hand, on like a product sense, they're like closer to catching up than ever, because it's sort of like the actual difference in how well they perform is smaller, but the difficulty in bridging that difference is a lot higher.
Yeah, it's sort of like, we're at the top of the sigmoid.
Yeah.
Everybody was modeling it was going to be an exponential, it was going to go up forever. It's like, no, that nothing's like that. Like it goes up for a bit and then it levels out and maybe it comes down or something. But like,
this is why I was always kind of skeptical of the Terminator narrative, is that all of these literally like every scientific field in history, every technology in history has reached this point of diminishing returns, right? Whether you look at industrial chemicals, whether you look at cars, whether you look at aviation, whether you look at drug discovery, whether you look at the personal computer, right? There's typically what's called an incubation period where the technology is getting better, where people are investing more and the productivity isn't really appearing, and then there's a burst in economic impact, and then there's a slowing down. And there's a similar thing, it happens a bit earlier, but there's a similar cycle with research, right? Where people are kind of investing in the research. There's what people in machine learning called like the machine learning winter, deep learning winter, AI winter, whatever, where people are doing actually very valuable research, but it's not really translating into any kind of practical or economic value. And then a point where all of that all of that research gets realized into like an actual product, and becomes enormously impactful for people, and that spurs more research. And then once again, that research kind of completes and finishes that cycle. Now, I think that a lot of the economic impact is actually still to be realized, that there's going to be a lot of economic growth still. But in terms of how purely, quote unquote, intelligent the models can get, I think that there's already been, a remarkable decline in progress. You saw that with the GPT-5 launch. You saw that with, Claude 4. You saw that with Llama 4. It seems like all of these labs, they're not so impressive. They're not matching the pace that they used to have. And I think that's honestly not really the lab's fault. I think that's more so a kind of fact of reality, especially since you're seeing that across all of the labs.
Yeah, I think the technique had a certain amount of juice in it, and we've been squeezing it harder and harder and getting less and less juice. But it's like, the transformer technique, the attention.
Yeah, and people thought, especially early on, that we'd be replacing the transformer sooner rather than later. And there have been small modifications. People use what most of the top labs use, what's called a mixtures of experts transformer now, which is a version of the transformer that essentially subdivides part of the network so that it's more efficient to run, but it's still doing, very practically doing the same thing.
Wait, can you briefly describe what is the transformer mechanism?
Yeah, so the transformer algorithm is essentially an algorithm published in 2017 by Google in a famous paper called "Attention is All You Need." And the idea behind it is essentially that the reason why it's called "Attention is All You Need" is actually quite interesting, because there were this other family of algorithms that you can kind of think of as like the near ancestor of transformers, which were RNNs, recurrent neural networks. And the idea was that actually that those algorithms were doing all sorts of unnecessary stuff, and the specific operation within those algorithms called the attention mechanism was, well, all you needed. So this attention mechanism essentially allocates, essentially like matches different values from one layer to the next layer. It does this using what's called a matrix multiplication, which is these, at scale, very expensive computations that are done using the NVIDIA GPUs, and it essentially creates these what are called features, which are not the same thing as like actual like features in ChatGPT, but are kind of like elements that are learned by the machine learning algorithm that are mapped through these various layers of nodes.
So tell me if I've got the right idea. So with attention, it's like a separate layer of neurons.
So you essentially have like several layers of neurons. The attention mechanism is the function that we use to essentially connect one layer to the next layer.
Okay, so you put an attention layer between each of the, like normally neural networks have layers, but you're kind of putting this attention boundary between them sort of to...
Or the attention mechanism is the thing connecting the layers.
Is the thing connecting it. And it's somehow selecting what's important and what's unimportant?
I mean, the ultimate outcome that it's trying to achieve, at least in the case of large language models, is what's called next token prediction, right? So the eventual outcome, the actual like output of the algorithm is like the next token, right? Which is kind of, you can kind of think of it as giving the next word. right? So you have as input, this is like the original function of the transformer. If you ever use like GPT-2, this is how it actually works, is that you have like half a sentence and it'll complete the sentence for you. So if
It's like an elaborate autocomplete.
yeah, exactly. And how that autocomplete would run is that the thing that you were trying to predict at the very end was the next word, and then you make a prediction, and then if that prediction is wrong, this is during the training phase. If that prediction is wrong, then or I guess if it's wrong or it's right, but if it's wrong, then it creates a response to kind of correct the error. And the way that response happens is through a method called stochastic gradient descent, which is essentially taking the derivative of the error and what's called backpropagating it. So taking the derivative at the layer that's closest to the end, essentially saying like, okay, this is wrong. What did I get wrong? What direction can I correct in? And then updating that layer and then moving that backwards. That's why it's called backpropagation to second to last layer, doing the same thing, correcting any errors that were made in the direction of getting it right the next time, and so on and so forth.
Well, and but what makes an attention layer different from a normal layer of neurons?
I don't know if this is the exact nomenclature, the exact reason why it's called that, but this is kind of like the best I can remember. It's like allocating what word, what you can infer from one word to another, right? So if you have, if you have a verb, what can you infer about the next word? Maybe it's like, I am going to do something, right? I'm going to do this. I'm going to do that.
So it's kind of like narrowing down the possibilities so that like you don't necessarily have to consider all the possible branching points. It's like...
Yeah. This is a very, very common theme in machine learning where you have this really open-ended search, right? And the question is, how can you narrow down that search? If you're kind of trying to consider like every single word and what word might best slot in, then that's just going to take way too much time, right? That's a very inefficient way to do things. So what other ways are there to do things, right? And the attention is kind of allocating that what you can infer. So you have one node, it's connected to the nodes in the next layer, but according to parameters that where if this node has a certain value, you can infer certain other things about the other words, and that's where the attention mechanism is taking place. And I think the thing that differentiates the attention mechanism from the previous recurrent neural network steps is that there was essentially like an additional step of processing. This is like why it was called a recurrent neural network that was ultimately removed. And it was like this longer feedback loop, and then the attention mechanism was one part of the feedback loop, and they made it just the attention mechanism.
So that was from 2017, you said?
Yeah.
And so, but it took, I guess, quite a few years before that really fructified into, and like, because GPT didn't occur until many years later, right? So
yeah, this was this fascinating pattern where the order of events is that OpenAI is founded, right, in like 2014, I think, and then 2017, the attention mechanism, which eventually paves the way for ChatGPT, is released, and then in the coming 5 years, they adapt that into first GPT-2, then eventually GPT-3, then they modified GPT-3 to make it more user-friendly, and that becomes ChatGPT, and goes ultra-viral.
So, I guess it took a while to not to implement it, but somehow because was there some other, I don't know, technique they had to do to make it work? I mean, because it sounds like
it was a few things.
It was a few things. Okay.
So first was just the compute resources. So one of the main differences between GPT-1, GPT-2, and GPT-3 was just the amount of data and compute that was used. So this is why NVIDIA is so wealthy and so valuable. Is that all these AI companies now, except for Google, I guess, all need to buy NVIDIA GPUs. Google has their own hardware, but it's a similar thing, right? And then OpenAI, there was this idea that you can make the AI models larger and larger, and this would increase performance, and it did up to a point. And so they made the models larger and larger. They went from GPT-1 to GPT-2 to GPT-3 by making them larger and larger, and by doing other kind of small under the hood things to optimize it, like what we were talking about earlier with quantization. And what actually really changed things, though, was that they started experimenting more and more with what we now call post-training, which are steps that you take after this very expensive training step where you kind of train it on all of the data on the internet. And the question that post-training is trying to solve is, we've been trying to get LLMs to be very generally good at things, to process text very generally, to understand kind of all of the human internet. What if we just wanted to do like a specific thing really, really well? Like, what if we just like really wanted it not to say the N-word? Which you can imagine, like if you're reading all of the content on the internet, maybe a recurring pattern in some cases.
Sure, right. Like not everything on the internet is equally sort of desirable. Like the AI models all kind of talk in this very kind of like fairly neutral tone and very helpful, like fairly formal sounding, and so that's not the average way that human beings speak to each other on the internet.
That exactly is the creation of post-training. So that's what we're leading up to, is that around like mid to late 2022, they really ramp up. OpenAI really ramps up, or this is when they publish. I would assume they were working on it earlier, but they really start publishing more and more with regards to post-training, with regards to how they modified their models to be more user-friendly. And part of this is even creating the kind of ChatGPT interface itself, because now we're used to, you ask ChatGPT a question, it answers your question. But that's actually not the natural way that transformers work. The natural way that transformers work is that you have a sentence and it completes the sentence. And the kind of golden bullet, or the silver bullet they were looking for in GPT-3 was what's called zero-shot completion. Zero-shot completion is essentially what we have now, right? Which is like, I ask you a question, you answer the question, right? ChatGPT answers the question. And why that's called zero-shot completion is that most of the time you would have to provide examples. So if you're using GPT-2, you would have to say, okay, I want you to add these numbers. Here are some examples. 10 plus 5 is 15. 11 plus, 23 is 34. You would give it a few examples, and then it would do much better. But they were looking at the time at zero-shot completion and creating the specific style of question and answer format. And the way they ultimately found how to do that is to take manually curated data sets, so kind of what's called supervised learning, have people create specific data sets designed around accomplishing a specific goal. And in this case, it would be like QA data sets, right? So it'd be like, here's a simple question, here's how you should answer that question, right? So it's essentially creating this pattern to specify in these later steps for ChatGPT to follow. That ChatGPT sees a question, it knows it needs to reply to that, not by drafting another question, but by or by continuing the question, but by actually answering the question. And that's done through these curated data sets.
So I mean, it's interesting. So and you call this post-training.
Yeah.
But in some sense, it is another step of training.
Yeah.
Right?
Exactly. The other joke people will make is that we have pre-training, which is like this massive step, this incredibly expensive step where you train on all of the data on the internet.
Okay.
And then you have post-training. You don't have training. But if you combine pre-training and post-training, that entire thing is called training.
It's a strange sort of backwards terminology, but I guess once things stick, it's kind of hard to undo them.
Yeah. A lot of like the twists of fate of like what we use, what language we use in like the machine learning community is just like random press releases by OpenAI. It's just press releases by OpenAI. That's the only reason.
Well, yeah, and you can see this in sort of, say chemistry or biology as well, where, the terminology is made at a time when like that was, the knowledge was incomplete and people discovered something new. They came up with a name. And then later there was maybe a refactor they could have done to make the terminology more, and sometimes this does happen, but also sometimes you end up having to roll with the old terminology. And then you get these sort of overlapping terms. It's not nicely separated and they sort of, contradict each other, or there's, and so, I as a programmer, I'm sort of obsessed with names. How do you name this function in a way that like sort of requires the minimum amount of context in order to understand what it does? Because a lot of times it's like, back in this like C programming days, you only had so many characters per line, right? So everyone you got in the habit of naming their functions and variables very tersely. It was just like one letter, two letters. And so then you had to like know a lot about what was going on to even interpret these names. And which is like, okay, like at that point, why aren't you just writing it in assembly, But
yeah, you need to know the memory,
yeah, and so this sort of like clean, and also like if it's a large code base, you're sort of just plopped in the middle of this thing, and it's like, I'm confused. I don't know what this function's for. What are all the places it's used? Why is it called this? And we're adapted to like live on the surface of the planet Earth, and we need oxygen, and we can't live underwater for very long without very specialized equipment, and there's all these sorts of things that you might consider part of intelligence that our body doesn't know how to sort of metabolize sunlight in the same way that a plant does, and so like, this dream that we're going to make a model that's going to know how to do everything extremely well, to me is like, it's sort of like, okay, maybe if you gave it, all possible, behaviors of the universe that were accurate as its training data, maybe it could be like much better than any human. But I think right now we're just training it how to talk like people, and it's quite a different thing,
at
right?
a practical level, for the kind of economic and like history of technology reasons we talked about before with the development curves, I think it's really unlikely. But it's actually a fascinating question why there was so much hunger to believe that, right? And Peter Thiel had this answer on a podcast recently where he said, AGI is like the only technology we have left, where before, if you refer to technology, it could be a car, it could be a plane, it could be all of these new chemicals and factories. It was like essentially like everything we have today would be something that someone in the 1800s would call technology. Now we say, or let's say like in the 2000s, we would say technology to refer to software, right? So any computer program was technology. And now I don't think we're quite there, but Thiel basically looks at AI as like the one thing people could hold on to still say that we're still making progress, that science hasn't stagnated, that our economy hasn't stagnated, that we haven't just stopped innovating things. The only example that people can really point to of something that can really change your life that we have left is AI. And that's his reason for why there's such an obsession.
So it's like the final frontier.
Yeah, it's like the last seed we have left. And we have to use this seed to seed our entire field, or we will have nothing.
Well, and there's also sort of like, building, having slightly better material science or having slightly better airplanes, being able to go further with less fuel. Like all these are sort of maybe, they're valuable engineering advances, but not necessarily fundamental breakthroughs. And
there's this tweet in reply to someone was like talking about, made a tweet about kind of what Marx would think of like contemporary socialists or something like that. And someone replied to him like, if Marx was reincarnated today, the thing that would surprise him the most is that we went to the moon, right? And the tweet was like, the moon in the fucking sky. And those kinds of completely world-changing discoveries, I agree with Thiel on this point to the extent that I mean there are other like promised things, and to the people who are trying to create those things, whether it's Elon going to Mars, whether it's like Brian Johnson trying to live forever, I like really respect the attempt. I'll wait until I see it, right? I'll wait until I see the final product. But really, I think AI is the only thing that people feel is close to being that kind of like we went to the moon in the fucking sky technology.
I mean, it's certainly impressive, to make sand think, and I think also I like the saying that technology is the crucible of science. It's like you've got all these cool theories. All right, cool. Where's your spaceship? All right, show me your spaceship. You got a spaceship? Okay, now let's talk about your theories. But it's sort of how do you prove that you know something about the mind as a species?
Or like a related data point is I think there was some. This is from like recent U.S. job statistics, but that like all of GDP growth in like the last quarter was either medical spending or AI data center spending.
Wow.
And that's,
It
that's pretty bleak.
It is pretty bleak.
It's like, will we build the AI? Will we have the AI renaissance first, or will we all just get drained dry by the healthcare system? Which will happen first? I don't really know.
Well, it kind of dovetails with Brian Johnson's "Don't Die" thing, which is interesting. I mean, you could see that as another frontier of like, okay, how do you dramatically increase human lifespan? And of course, on a sort of like public policy level, you might ask, is that even desirable? But but certainly, most people don't particularly want to die at the moment of death. I guess maybe suicide would be an counterexample to that, but. There's lots of evidence that we don't fully understand the world. I think there is this kind of like Graham Hancock talks about this sort of delusion of science that like we have this kind of feeling that like we have it almost all figured out. We're just like just a couple more pieces, but there's actually like these kind of quite severe gaps in like if you start learning about cosmology, God bless those people, and all their valiant efforts to understand the universe from this tiny little, ball we're sitting on. But like, there's so many like just gaping holes in the story, and it's not their fault. We're trying to, infer very huge stories from, tiny little perspective. But to me, it's like when those gaps get closed, each one of those is a scientific revolution that's probably going to have, potentially dozens of new technologies that arise from it. And a lot of this stuff, I mean, I'm reading this book, Cosmos and Psyche, and it starts off talking about how like the whole shift from geocentrism to heliocentrism, where they thought the Earth was the center of the universe, then they said, oh, it was the sun.
Yeah.
And how that was such a profound shift in people's thinking, but also like the early people who believed that almost had to be a little bit delusional because it was in direct contradiction to everything their senses said. It was like everyone's like, you don't think the Earth is the center? Look around. It's right here. It's right here.
Yeah,
and like,
yeah.
and like, look,
That's
did
fair.
you see
Yeah,
the
that's a
sun
good
go
point.
up over there? So you had to be quite a sort of radical thinker. And of course, it doesn't mean every radical thinker is like, glimpsing some breakthrough. But, there's lots of delusions when you're considering, when you're questioning your own assumptions. But so what now? I mean, like we've got,
That really is why, I'll speak for myself, why I'm here at the Network State. There's this open question that Thiel asks in 0 to 1, but also in a lot of more recent podcast appearances. He seems more and more worried about this. Of like, is the narrowing of progress, is that like a piece of reality, or is that a choice? Right? Is there something we, humanity, the U.S. government, individuals, is there something we've done to make this progress narrow down, make it so that we have to rely on AI as like the only thing, or is it just inevitable? And when I was growing up, when I was much younger, when I like first read 0 to 1 at like 15 or 16, I think. I didn't really think, to be honest, but it was my natural assumption that this was just the way things went, that things were declining, and to be fair, in like existing fields, that is the pattern, right? But at the same time, there have been many pieces of history where we've been able to invent more and more new things, and we've been able to kind of start new fields faster than the old ones were running out, and that was really the Enlightenment. That was really the scientific revolution. That was really the first and second industrial revolutions, right? That's their defining characteristic, is that we were able to invent more and more new things to get started at the bottom of the S curve faster than the old ones were running out. And why aren't we doing that anymore, right? Or why aren't we doing that outside of maybe just AI? And I think that at least it's hard to get down to one answer. But I think at least one of several answers, maybe the most important of several answers, is that we've decided as a society to stop rewarding new things.
Well, I think there's a natural. There's this term some people use of neophilia and neophobia, That maybe there's almost like a
yeah.
personality trait some people have of being like, fascinated and extremely curious and wanting to learn new things. And some people have a trait of more of like, okay, I kind of like, I'd rather be in my safe zone. I feel comfortable here. It's dangerous out there. And of course, there's also the saying, curiosity killed the cat. I mean, sometimes you stick your nose in some new place and get bit. When I think about this scientific revolution thing, I mean, you're talking about, it seems like things are decaying. I mean, like in some sense, yeah, we're all getting older, and all the cities are sort of, the buildings are, getting, the room is a little bit dirtier than it was last month, and it's the paint on the walls is a little bit more faded, and I mean, like this entropy is happening all around us all the time, but the game we're playing is like, how do you sort of like stay out of the claws of the tiger?
It's the air conditioner of the universe.
Look, I don't know why the air conditioner always breaks. And I'd also like to know why when I press power, it doesn't shut off the first time. I have to like be like, no, it's okay. You can really shut off. It always takes 2 or 3 times to shut. It beeps.
Oh, interesting.
But it doesn't turn off. And it's across multiple companies that have made this strange feature. And they're like, you probably didn't mean to turn it off. You want to keep it on, right?
Surely you would like more air conditioning.
Well, and also what I'd like if we have a civilization that doesn't just like disappear after 1,000 years.
Yeah,
that would be pretty cool.
nice. Yeah.
Can we make a civilization since we already know everything because we're amazing humans? Can we make a civilization that lasts 100,000 years? Let's just have that as a milestone, right? You think you know what you're doing, humans? All right, yeah, you're such a smart species. Oh, amazing, right? Try not to blow yourselves up every 200 years.
Yeah, and it feels like the kind of more confident people are about science, the more they'll lead to these civilizational disasters, right? We kind of think in hindsight, and that this was to a large degree true, that we're much more technologically advanced than the Soviets, but that wasn't really the perception at the time, right? With Sputnik moment, they got the first satellite. They were at least competitive in terms of physics and in terms of going to space. There were many great Soviet mathematicians. And the idea was that, the Soviet Union was this new, more scientific way of creating a country, that it wasn't created based on the superstitions of, random ex-Englishmen in the 1700s. It was created based on science, that we had, we understood human society, we understood human civilization, and this was going to be the best civilization.
Yeah, my PhD advisor was a Soviet era mathematician, and he said, when I was in school, they made us take a course called scientific communism. He said, why did they put the word scientific there if it was science? And I was like, you don't take scientific chemistry class, let's go take a scientific physics class. No, it's actually science. But, you can, how you sell things really matters, especially if nobody's looking inside the box. Maybe.
Yeah, and you see this, I think this kind of science branding, it boxes out the ability to do actual science. Where if you have these questions, or if you have these like proclamations that you can't question, if you have these decrees, if you have this, quote unquote settled science that's not actually settled, right? If you have these models of economics or psychology or sociology or political science or so on that are really based on assumptions that haven't been questioned, and where all data that is collected is, forced to fit these models, and you don't actually ever question the assumptions of these models, and then these models always have grievous errors, and the answer to that is always like, we just have these imperfect models. We just expect all models to be broken. When you have these like unquestionable standards set at really like low performance levels, then that's actually not science being done. That's like science being prevented from being done at any cost.
Right, it's sort of like it's a weight in the model that simply can't be updated.
Yeah.
Because my grandma made that weight, and that's the best weight ever. Like
yeah. My grandma's neural network weight.
That's right.
That's a vibe. So the good old neural network weight.
Listen,
passed down.
Yeah, my daddy put money on that weight, and and I can understand the wisdom of like, okay, maybe some weights should be easier to update than others. like, because maybe it's more dangerous to update certain things. So there's like, the gnomic game of of government, where it's like, okay, you have like local laws which are maybe easier to change, and then there's like federal laws that are harder to change, and there's the Constitution, which is like very hard to change. And likewise, we have the brain has these layers, and like it's a lot easier to sort of rearrange the sort of symbol learning than it is to like relearn how to eat, or change how you how you have sex or something. Like those are like pretty deep in the machinery, and if you edit them, like maybe you could make it better, or maybe you could just kill the thing. It's dangerous to like this is why I think I lived in America, and I saw like all the kind of bad relationships people have with food, and particularly, some people, like, they were eating this like food that wasn't very good for them, but, and they realized it, but it was sort of like, it was hard to actually change that behavior. And it's, like the mouth is such an ancient part of our physiology in terms of like everything has a mouth. Like even like unicellular organisms kind of have mouths, and like, so like, the animals have mouths, the reptiles have mouths, right? So the mouth is like this like really old piece of tech that like no one's really sure how it works. It's kind of like just does its own thing by its own. It's like the baby activates. It's like mouth, and then it's like, okay, all right, put it in the mouth. Like that's what we do. Just put it in the mouth, and then so then it doesn't require the neocortex to get involved. And I think it's largely segregated from the neocortex. I think most people just like have like mostly automatic things that they do when they eat. Like, oh no.
Part of it is also that there are many conservatives who now are reaching towards Plato or Aristotle to kind of redefine their like new version of conservatism. But the idea is that Plato, of course, not a fan of democracy, would criticize some of the some of the policies of the day, believed in aspiring towards a higher human nature, that you needed to control yourself, that to some extent you needed to control the population to push them towards a kind of higher moral duty. You don't have to agree with that. Of course, there are some things I disagree with, some things that I agree with. But I think like the order of what things we can change about ourselves is really flipped, especially in America. This is my perception, where the things that are most granular are the things that who cares if you like radically change your diet? Who cares if you radically change the way that you have families, so on and so forth? These like very ground level, individual or small group things. That's the things that are, ultra fluid, ultra liquid, whatever, completely no restraints whatsoever. I'm not saying there should be legal restraints, but you should consider, you consider the health of your family, and you should consider the health of your children and your siblings and your parents and so on, right? I mean at a social level. But the things that absolutely cannot be questioned are, kind of what is morally good, what is the political good, what kind of political systems should you support, what kind of wars should you support. Those are the things that, absolutely cannot be questioned. And there's a kind of political explanation for that, right? That you can't question those things because that actually affects power and the kind of personal, the personal things. You can kind of flip those around and not really change who's in power. But in terms of just how you live your life and how good your life is going to be, and really like the health of the country as a whole, I think they've completely reversed that order of priorities in terms of what you can and cannot change.
I was thinking about how like banks, right? This is like this old like ossified centralized system, but like for example, the quantum issue of you're supposed to update your cryptography to address the quantum threat. For a bank, it's actually pretty easy. All they have to do is they go in and they control the database, and then they control everyone's wallets through the phones or the websites. And so they can just basically with all at once force everyone to update, and blockchains don't have that luxury. And so you have this sort of like we're exploring the kind of what are the advantages and disadvantages of these various approaches. You have highly centralized ones, like say for example like the Chinese government, where they can like snap their fingers and then like everybody does something, versus like in the West they have they can just debate endlessly, and get nothing done for years on end, and everything becomes about like opposing the other half of the country. And
what you basically said before is basically what most ancient or kind of early modern political philosophers would have thought, right? That centralized authority has the benefit of speed. And at the same time, their main drawback is like, what if you have a bad king, right? What if you have an authority, you have that very same speed, but instead of upgrading people to the correct level of cryptographic security, they're, starting a communist revolution, or, just imposing a diktat that creates a famine. And when you have this kind of modern network, it's actually an open question, not how quickly it will progress proactively necessarily, but how quickly it'll react. So if there's
what's the learning rate?
Yeah, exactly. And you've seen these massive cascades, for both for good and for bad, interestingly, but I would say more so for good, that just happen widespread across these hyperconnected networks, right? Like, you could see. Actually, there was a recent problem in a node package, and I think literally within hours of that being discovered, like I got several pings on it on Discord. We kind of fixed it right away. I think probably like upwards of 1 million people around the world easily, maybe 10 million, maybe more, corrected that like immediately.
Yeah, I think I read the hacker got like $50 out of it. Like that was it could have been like a multi-million-dollar payout, if they got the right target, but everyone reacted very quickly, and that was kind of a hive mind security thing.
Yeah, and so you have these like protocols, you have these systems of exchanging information where even though it's decentralized, even though we don't have a king, right? You get these massive like you could say hive mind, right, like reactions, but I think also you can say that each individual there is acting in their own interest. But you get these massive cascades across the entire network, and so I think it is a bit of an open question of whether these new networks, whether they're blockchains, whether they're decentralized states, network states, whether they're other decentralized communities, we actually don't really have a live fire test of like someone trying to take down some of these networks before they can react as soon as possible, right? This is like an open question. This is something that I think we'll learn in our lifetimes, of whether of whether the Bitcoin network or whether the Ethereum network or whether any of these networks, whether the internet itself, right? Whether the global community of Node.js developers has the speed of a king. We don't know. We'll find out.
Well, I really appreciate you coming on the show today. It's really been interesting. And if people want to find out more about what you're up to, where do they find you?
So Network School is ns.com. You can come here, you can experience it in person. My personal writing is at fromthenew.world. And yeah, and you can find me on X as well at Brian Chau 57.
I think that's a wrap.
Awesome.